Okay, now here we are moving to a big, huge idea. And that is putting everything together. What we've learned about shape, what we've learned about polarity, and what we've learned about attractions between molecules to really help us understand the properties of molecules. The next two lessons will be ones that you'll rely on in biology next year because you'll have to understand how the molecules in your body or in nature act based on their polarity. So, and their shape and all these things. So, in a polar bond, the more electronegative atom has a partially negative charge. It is the one that is pulling more tightly on the shared electrons. The less electronegative atom has a partially positive charge. It is the one that is sort of giving up more. It can't hold on as tightly. So when you are looking to determine the polarity of a molecule, look at the surface atoms. Don't worry so much about C. Because carbon is going to be in the middle. So you really want to look at the things attached to carbon. In proteins have huge molecules, and you can have different areas on the surface that are different, that are polar or nonpolar. But we're going to really focus on small molecules. And if we want to look at if a molecule is polar or nonpolar, here's what we can do. 1, check for bond polarity. So look, do you have polar bonds in the molecule? So if you have O2, well, then you know you don't have polar bonds. If you have CF4, well, then you know you do have polar bonds because the difference in electronegativity between carbon and fluorine is very high. So check symmetry. For number 1, check for bond polarity. All bonds nonpolar? Well, then your molecule is nonpolar. Polar bonds equals go to step 2. All right. Step 2, you check the symmetry. So are all the atoms on the surface arranged symmetrically? This is where shape becomes really important. And then yes is nonpolar. No is polar. So what does it mean for a molecule to be symmetric? Well, let's look at something like CF4. I said a moment ago that CF4 had polar bonds. The difference between them in electronegativity is about 1.5. But if I ask you to do the shape of this, well, you look, there's 4 domains, and they're all bonded to, and it's bonded to 4 atoms, so that's a tetrahedral shape. So if I draw it out, well, everywhere around the outside, everywhere around the outside, I don't want black. Let's do blue. Purple. It's all the same atoms arranged symmetrically around the outside. So that molecule, there's no way you can go just from plus to minus through the molecule. All of the outside has the same partial charge. So this molecule, even though it has polar bonds, is nonpolar because the shape is equal throughout. All right, so let's go back to HCl. HCl, first we look at the bonds, H and Cl, compare electronegativities. It says Cl is 3.16. I think our numbers are a little different than the ones here. But we'll just use these numbers. 3.16 for Cl, 2.1 for H. So Cl is stronger. The electrons that are shared are pulled closer to Cl, so that's going to be partially negative. H is going to be partially positive. We can draw an arrow from plus to minus. This is the simplest molecule to be able to pick out polarity. So if you can draw the arrow, this is a polar molecule. It's got one end that's partially positive, one end that's partially negative. If it's only two atoms, it's pretty straightforward. Okay. So electronegativity, once you have more than two atoms, you need electronegativity and the overall symmetry of the molecule to determine polarity. So here we have formaldehyde, CH2O, where the 3D shape, if we do the Lewis dot structure, you'll see you have this. So 3 domains, 3 atoms that it's bonded to. That means you have the flat triangle shape, or trigonal planar. If we look at our electronegativity values, O is much stronger than C, which is even stronger than H. So the electrons are getting pulled toward the oxygen, leaving it partially negative on this side. The H's are partially positive. We can draw an arrow from plus to minus. This molecule is polar. With NH3, so NH3, if we draw the Lewis dot, I should have drawn it a little bit differently, but that's okay. So 4 domains, 4 sides covered, 3 of which are bonded to atoms. 1 is a lone pair. So this is our tripod shape, or trigonal pyramid, where N, the top side, N is more electronegative than H, so N is pulling the electrons closer to it. This side is going to be partially negative. This entire bottom side is going to be partially positive. So you can draw an arrow from plus to minus. So the molecule is polar. Now when we get to a trickier one. If the overall shape of a molecule is asymmetrical. So here I have CF3 or CClF3. This is not a symmetrical molecule because the Cl is on one side, so our outside, our surface, is Cl, F, F, and F. If it's made from more than one kind of atom and it's asymmetrical, chances are it's polar. This is a little more complicated than what I'm going to ask you because this is tricky because Cl is still more electronegative than C, so you might think it might be partially negative, but because the F is so strong, it's not. But asymmetric, more than one kind of atom, it's probably going to be polar. Now, you might have heard this idea that like dissolves like. So substances with compatible intermolecular forces will dissolve in one another. And we'll talk about this when we're doing solutions later on in the year again. But so we know NH3 is polar. H2O is also polar. So only polar molecules dissolve in water to a large degree. Because if you can look at the way the water molecules surround the ammonia, the NH3, well, we have the partially negative parts of the water are attracted to the partially positive parts of ammonia. Positives and negatives attract. The partially positive part of water is attracted to the partially negative part of ammonia. So basically what's happening is you have the water molecule sort of surrounding the ammonia, and because they have partial charges, they have something to be attracted to. The water molecules can attract the ammonia because of the partial charges. So again, I forgot to take the smell part out of it. So we're going to talk about what does polarity have to do with shape. Well, differences in electronegativity can be used to determine the direction of polarity of an entire molecule. So really what you're looking at is if it's symmetric, it's nonpolar. If the bonds are nonpolar, your molecule is nonpolar. If you have polar bonds and it's asymmetric, your molecule is polar. And we're very happy that water is polar. Otherwise, it would not be attracted to itself, and it wouldn't be a liquid. So molecules that are asymmetrical in shape and composition are usually polar. Don't worry about the smell part, although it is true. And also, the last bit, polar molecules dissolve in other polar molecules. And nonpolar dissolves in nonpolar, but not nonpolar in polar, or polar in nonpolar.